Hi everyone, this is our first video on our waves unit. You should be taking notes on this video, not just on what's written down on the slides, but also on some of the things that I'm actually saying. So our essential question in this video that we're going to answer is, what is a wave and what properties do all waves share? So what is a wave? Well, waves are actually just energy that are moving through the space around you. There are two properties that all waves share. The first is that a wave has to have a wave source. So a wave source is something creating a vibration that is essentially the source of the energy that that wave is made out of. All waves also have to have some sort of medium. And we use the word medium to describe the material that the wave is in. A medium could be a solid, a liquid, or a gas. And some waves can actually travel through space itself, but they need something out there that they're traveling through. In our example below, what you see is a wave that's traveling through a piece of string or a rope. And that piece of string or rope is actually the medium. So the wave is traveling through the piece of string. And what you'll notice is that that energy, as it moves through the medium, as it moves through the string is actually not moving forward. If you look at that little dot, where the little finger is pointing, that dot just moves up and down. So the medium might move up and down, it might move, compress and come back together, but the medium is not actually moving forward through the string. It's just that the energy is moving through the string. Some of you may have experienced this in your own life if you've ever been swimming in the ocean. And when a wave comes through, if you're far enough out, you will feel it lift you up and then make you go down again. You are part of that medium of the water, and the energy is moving past you or through you as your particle goes up and then comes back down. Here are a couple other examples of waves and their sources. So maybe you jump into a swimming pool, right? The source of this wave energy is from you jumping into the swimming pool. You are the source of the vibration traveling through that water, okay? And that means that the medium or the material that the vibration is going through is the water. So you're the source and the water is the medium for that wave that you create. Another example could be one of these candy wave machines that you could actually make yourself with some gumdrops and some bamboo skewers and tape. We have one at school. So in this case, the wave source, the thing that's creating the vibration, is this physics dude's hand. He's giving it a little tilt, okay, that's causing that wave energy to propagate through the candy wave machine. And the medium that it's traveling through is just this collection of gummy bears, chopsticks, and some tape. Wave sources can create two different shaped waves. The first animation in the top part of this picture shows a wave pulse. And a wave pulse is this single crest or single trough that moves through a medium. A wave that looks like a wave pulse could be like a tsunami. So when we have an earthquake and the seafloor punches back up on the bottom of the ocean, it creates pretty much a single pulse wave that then moves through the ocean as this big peak headed towards shore. Okay, so you can have a wave pulse. You can also have what's called a periodic wave. And a periodic wave is when you have a whole bunch of full waves, so crest, trough, like the animation at the bottom, that kind of continues on and on and on. So this would look like something like if you're standing holding on to a jump rope and your friend has the other end, and your friend is making it go up, down, up, down, up, down, up, down. It will send a periodic wave all the way to you. So like I mentioned before, a wave pulse is generated from a single burst of energy from a wave source, and that pulse or burst moves from one side of a medium to another side. So if you cannonball into a pool, it's going to send out one big wave in all directions to the other side of the pool. We can measure the energy in one of those pulses of the wave by measuring its amplitude. So how high from equilibrium the wave crest is. So just looking at one of these pictures below, I'm going to try and draw the straightest line I can. That's not very straight, along that sine wave. So equilibrium is like the middle of the wave. And if you're measuring the amplitude, a positive pulse is measured in the up direction. So this side would be a positive amplitude. This is going to be a negative pulse measured in the down direction. Wave pulses can come in a variety of different shapes, as you can see in the pictures below. And the shape of the wave pulse is really just dependent on the movement of the wave source. So it has to do with whatever the source is or the thing is that's creating that vibration. When we talk about the term wave propagation, what we're really referring to is the direction that the material is moving compared to the direction that the energy pulse is moving through the material. Okay, so here's an animation showing the two wave propagation types that we're going to be focused on in this class. The first example above is what we call a transverse type of propagation. And in a transverse propagation, the energy is moving from side to side, right, through the slinky, but the individual slinky links themselves, which are the medium, are moving up and down. As that wave propagates through, the material moves up and down. So we say the medium is vibrating perpendicular to the direction that the wave is headed. And what this looks like is as that energy moves through, the slinky links move down and then they move up. They're doing this sort of jiggle. In a longitudinal wave, like the example below, the medium, the slinky here, is moving in the same direction as the wave is propagating. So the energy is moving through the slinky like that, and the individual little slinky links are just squishing and coming together. So expanding and contracting, but they're squeezing in the same direction that the wave is moving. So we're saying the medium vibrates parallel to the wave velocity. So as that wave comes through the longitudinal wave, okay, it goes that way, and then it squishes back the other way, and then it goes forward. So it's squishing and expanding, squishing and expanding. These aren't actually the only two wave propagation types out there. There are others like Rayleigh waves, which have a circular motion to them, and there are some earthquake waves that have that circular motion. Torsional waves have a twisting motion, but these are kind of like the key ones that cover lots of different things you see in nature and in your life. There are four key parts to any wave, and we're going to look at them in this picture below. So the first part is the crest, and the crest is right here. Peak or crest, you can call it either one. It's kind of the highest point, or it's the highest pressure location in a wave. So it's where the particles are being squeezed together the most. That's the peak or crest. The next one is the trough, which is just the same amplitude, but in the negative direction. Usually it's the lowest point on a wave that looks curvy like that, or the lowest pressure point if it's a pressure wave. The amplitude refers to what we were talking about before. It is the height, so how high from this equilibrium line When you measure the height of it, it's also over here on this diagram. It's the same thing. And it's representing the amount of energy that that wave is carrying with it. And then a cycle. And the cycle is just a way of saying one complete cycle of the wave from a full crest through a full trough. I would pause the video here and draw a picture of this diagram in your notes. As I mentioned before, wave amplitude is related to how much energy is in each wave pulse. And because waves are energy, and we use waves all the time to move energy from one place to another, whether we're speaking or sending electromagnetic waves, radio waves, wave amplitude is really, really important to understand. So one example of something that's low amplitude would be like a baby talking or splashing, even the physical waves in the bathtub. High amplitude tsunami, right? You have a lot more energy in a wave like a tsunami than a baby splashing in a bathtub. Please take a minute to revisit the essential question of this video, which is what is a wave and what properties do all waves share? Remember that going forward, I'm going to be asking you to submit your notes summaries as part of the asynchronous attendance assignment. And here's a Calvin and Hobbes cartoon. Maybe some of you can relate to this from when you were a kid.